He would give the universe its grammar. But the man who organized the elements was born into a world of pure chaos. This story begins not in a pristine laboratory, but in the vast, frozen silence of Siberia, a place where winter lasted half the year and science was a distant rumor. He was the 17th and final child of a provincial school director, a boy named Dmitri, born in the remote town of Tobolsk in the winter of 1834. His future was not written in the stars, but in the grit of a mother determined to defy their reality. The first catastrophe struck when Dmitri was barely old enough to remember it. His father, Ivan Pavlovich, a man of philosophy and enlightenment, began to lose his sight. The darkness descended swiftly, relentlessly, until he was completely blind, forcing him from his teaching post and plunging the sprawling family into poverty. Their world collapsed. The steady income vanished, leaving only the biting Siberian wind and the gnawing uncertainty of their future. It was in this moment of crisis that his mother, Maria Dmitrievna, revealed an unbreakable will. A descendant of merchants, she possessed a practical resolve that bordered on ferocious. With a blind husband and a legion of children to feed, she refused to surrender. Instead, she turned to a derelict family property, a forgotten glass factory in the nearby village of Aremzianka. Maria poured her life into reviving the ruin. She battled debts, sourced materials, and managed workers in a place where industry had long since died. Young Dmitri spent countless hours there, not as a child at play, but as a silent observer. He watched the raw, chaotic dance of creation. He saw sand and fire, two simple things, merge in the roaring furnace to become something new, a clear, liquid mass that could be shaped and controlled. In the hiss of cooling glass and the glow of the kilns, he witnessed a fundamental truth: from a jumble of ingredients, a predictable, ordered substance could emerge. The factory became his first classroom, the transformation of matter his first lesson. The meager profits from the factory were barely enough to survive, and the education available in Tobolsk was a dead end. Maria knew this. She saw a unique spark in her youngest son, a restless curiosity that the Siberian plains could not contain. So, she made a decision that seemed an act of sheer madness. In 1849, when Dmitri turned 15, she sold their belongings, shuttered the factory, and set out to take him to the capital. Their destination was Saint Petersburg, a world away. The journey was a brutal, 1,300-mile odyssey on a horse-drawn cart. They traveled without money, without connections, without any guarantee of success. For nearly 3 months, a mother and her son pushed eastward through the Siberian wilderness. They crossed frozen rivers, navigated treacherous bogs, and endured the relentless blizzards of the Ural Mountains. They were exhausted, frostbitten, and perpetually hungry, but Maria's faith never wavered. This grueling pilgrimage was her final, desperate investment in her son's mind. St. Petersburg met them not with open arms, but with the cold indifference of a sprawling, imperial city. The cobblestone streets were damp, the air was thick with fog, and every official door was closed to them. They were penniless provincials with no influence. They lived with distant acquaintances, surviving on scraps and sleeping wherever they could find a corner. Every university rejected Dmitri. He lacked the right paperwork, the right background, the right everything. Yet his mother persisted, her determination a force of nature. She begged, argued, and finally secured an audience with the director of the main pedagogical institute, one of the few schools where tuition was free. As an exception, a final chance, Dmitri was allowed to take the entrance exams. He passed. He was in. The boy from the frozen edge of the world had earned a place in one of the nation's premier scientific institutions. His new life began in a cold, damp dormitory room where the windows were sealed with paper to block the drafts. He lived the life of a pauper, subsisting on poorly cooked porridge and stale bread. His uniform was a threadbare overcoat, his shoes worn through at the soles. Fellow students recalled him shivering through lectures, often sleeping in his coat for warmth. He had fought his way from the Siberian wilderness to the heart of Russian science. But the greatest battle was not behind him, it was raging inside his own body, threatening to extinguish the fire before it could ever truly burn. The Siberian cold was more than a hardship, it was a predator. Constant exposure, malnutrition, and exhaustion finally broke through his defenses. His body, already pushed to its limits, began to fail. A persistent cough racked his thin frame, and a feverish heat burned behind his eyes. The diagnosis was a death sentence in the 19th century, tuberculosis. Doctors gave him months, perhaps a year, to live. They insisted he abandon his studies in the damp, unforgiving climate of St. Petersburg. His only hope, they said, was to go south. In the winter of 1850, Dmitri was sent to Crimea. He traveled first to Simferopol, then to Feodosia, trading the frozen corridors of the institute for the sun-drenched shores of the Black Sea. Surrounded by the scent of salt air and the relative quiet, he spent nearly a year in a state of suspended animation. The illness receded, but the proximity of his own mortality had touched his consciousness for the first time. It left a permanent mark. Yet, even exiled from his books and laboratories, he did not waste a single day. He read. He devoured everything he could find. He read in Russian, French, and German, comparing scientific articles, making meticulous notes, and thinking. It was here, staring out at the endless sea, that a new sensation began to take root in his mind. He later recalled it as the first inkling that behind the staggering diversity of the natural world, the salt in the water, the minerals in the rock, the air in his lungs, there was a hidden unity. A single, elusive law governed it all. He returned to St. Petersburg in 1851, not as a frail invalid, but as a man forged in the crucible of his own near demise. The illness had not instilled weakness, but a ferocious will. Life had granted him a second chance, and he was determined to use every second of it. He attacked his studies with an incredible, almost frightening, focus. He worked through the night, spent every spare moment in the laboratory, and lived on almost nothing. His diet often consisted of little more than dry bread crusts. One story tells of him surviving for a week on a single loaf of bread and 2 mugs of hot water, refusing to spend the few kopecks he had saved for a new textbook. He bore these deprivations without complaint. His concentration was so absolute that fellow students and professors, who once saw only an awkward and withdrawn boy, began to regard him with a new respect. The diligent student was transforming into something more. He was becoming a true researcher, a man capable of seeing the universal in the particular. He started asking questions that others didn't. Why are some gases lighter than air? Why do certain metals react instantly, while others require intense heat? And most importantly, why do the properties of some elements repeat with such startling regularity? The Institute's modest laboratory became his sanctuary. Here, he conducted his first independent experiments, measuring densities, analyzing solutions, and recording his observations with obsessive care. He was less interested in the flashy reactions, the pops and fizzes, than in the internal laws that governed them. The seed of his future system was germinating, an intuition he could feel but not yet articulate. His professors noted his extraordinary thoroughness. He didn't just complete assignments, he interrogated them. He rechecked formulas, recalculated experimental data, and searched for errors where none were thought to exist. As one instructor remarked, this Mendeleev doesn't just want to know. He wants to understand. By the time he graduated with distinction in 1855, he was recognized as one of the finest minds to pass through the Institute's halls. He was offered a comfortable teaching position at a provincial gymnasium, a secure future. He refused. He wasn't interested in the classroom, he craved the laboratory. He chose to remain in St. Petersburg, to stay close to the libraries, the scientific community, and the tools of his trade. He chose uncertainty. He chose the search. After securing a position at the Institute to prepare for a professorship, he received the opportunity of a lifetime, a chance to study abroad. In 1859, he traveled to Heidelberg, Germany, a global epicenter of scientific research. Here, the world's most promising young chemists gathered to learn from giants like Robert Bunsen and Gustav Kirchhoff, men who were pioneering experiments with a previously unimaginable precision. But Mendeleev quickly realized that attending lectures was not enough. He rented a small apartment and, in a spare room, built his own private laboratory. It was a humble setup: an alcohol lamp, some flasks, a precise scale, and chemical reagents, but it was as he returned to Russia in 1861, a man changed. The intellectual ferment of Heidelberg had sharpened his mind, but his core remained stubbornly Russian, grounded in the tangible world. He immediately defended his master's dissertation, a work not on some esoteric theory, but on the interaction of alcohol and water. It was a meticulous study, a deep dive into the seemingly mundane. The work was praised for its experimental rigor, but more importantly, for its attempt to find theoretical meaning in the most ordinary of chemical processes. It was a perfect encapsulation of his scientific soul, a belief that universal laws were not hiding in abstract thought experiments, but were woven into the fabric of reality itself, waiting to be observed. Success came quickly. He was invited to teach, first at the Saint Petersburg Technological Institute, and then at the prestigious Saint Petersburg University. Here, in the lecture halls, he became something of a phenomenon. He was unlike any other professor. He never used notes. He never droned on with dry dogma. His lectures were alive. They were performances of logic and passion. He spoke smoothly, weaving in practical examples from industry and vivid anecdotes from the history of science, sometimes punctuating a complex point with a fresh joke gleaned from his correspondence with European colleagues. Students flocked to his classes not out of obligation, but out of genuine curiosity. He demanded precision in their work, yet he celebrated unconventional thinking. He believed a teacher's duty was not merely to transfer knowledge, but to cultivate a scientific worldview, to teach the very ability to see the world through the lens of inquiry. While his reputation as an educator grew, his true work continued behind closed doors. The university provided him with his own laboratory, a sanctuary where he could pursue his private obsessions. There, surrounded by the tools of physical chemistry, he meticulously investigated the nature of matter. He studied the pressure of gases. He charted the behavior of liquids. He measured specific gravities and rates of evaporation, compiling endless tables of data. Each measurement was a word, each calculation a sentence. He was building a new language to describe the physical world, constructing logical chains that linked one observation to the next. This relentless accumulation of facts ran parallel to his search for a grander synthesis, a unifying theory that would one day form the bedrock of his life's work. Mendeleev was forging a unique style of scientific thought. He was dissatisfied with mere observation, yet he refused to substitute real experiments with speculative constructions. He possessed the rare ability to see the universal in the particular, without ever losing sight of the concrete detail. His approach was a synthesis. It blended the empirical with the theoretical, quantitative analysis with qualitative observation, cold rigor with fiery intuition. His interests were boundless, spilling over from chemistry into physics, mathematics, geology, and even the philosophy of science. He corresponded with historians, debated the meaning of scientific truth with his peers, and championed educational reform. He was deeply embedded in the intellectual life of his time, yet he maintained a singular focus on the deep, underlying patterns of the universe. It was during these years, while examining the properties of substances, that he began to notice whispers of a hidden order. He saw families of elements that behaved in similar ways. He jotted down observations, made notes in the margins, and compared the atomic masses of elements with recurring properties. It wasn't a theory yet. It wasn't a system. But it was a direction, a powerful intuition that nature was not a chaotic jumble, but a structured, intelligible entity. By the late 1860s, the central question that had troubled chemists for decades began to consume him. Was there a fundamental law governing the properties of the elements, or was their collection simply a random assortment? Science knew of roughly 60 elements, a number that grew with each passing decade, but a system to understand their relationships was completely absent. Previous attempts at classification had been made. Scientists tried arranging elements by atomic mass, by valency, by external similarities. But every scheme proved fragile. A new element would be discovered, or a more accurate atomic weight calculated, and the entire structure would collapse. In one system, iodine had no place, in another, tellurium. The chaos felt absolute. Mendeleev felt, with an unshakable conviction, that an inner unity must be hiding behind this bewildering diversity. Nature, he believed, could not be meaningless. If substances had properties, there had to be an order governing those properties. This quest became the central task of his scientific life. The catalyst was practical. He was writing a comprehensive textbook, The Principles of Chemistry, and he hit a wall. How could he present the chemical elements in a way that was not just a list to be memorized, but a true reflection of their nature? He abandoned the text. He took out a stack of blank cards. On each card, he wrote the name of a single element, its atomic mass, its density, its valency, and its characteristic compounds. He laid them out on his great desk in his study. He began to play a game of cosmic solitaire. He shifted them, grouped them, compared them, searching for a repeating structure. Hours turned into days, days into weeks. His study became a storm of paper and ink. He would write, cross out, and write again, sketching tables only to discard them. His servant would bring him tea that grew cold as he sat, hunched and frowning, shuffling the elements, trying to find the one true order that satisfied not just logic, but with logic. He was trying to hear a rhythm in the silent data, a pattern that he felt must exist. Then, it happened. Not in a flash of divine insight, but in the exhausted surrender of a mind pushed to its absolute limit. After 3 days of relentless work, barely stopping for food or rest, he collapsed at his desk. In the fuzzy space between wakefulness and sleep, the chaos of the cards in his mind's eye finally settled. The dream that followed became legendary, but Mendeleev himself dismissed the mysticism. It wasn't magic. It was the final, critical synapse firing after weeks of obsessive labor, the moment his subconscious solved the puzzle his conscious mind could not. He saw it. A complete table, where every element fell into its rightful place. Waking with a start, he seized a piece of paper and scribbled down the arrangement he had seen, the structure that had haunted him for so long. In the early spring of 1869, he stood before the Russian Chemical Society. He presented not a finished law, but a preliminary sketch, modestly titled An Attempt at a System of Elements, based on their atomic weight and chemical affinity. The core principle was deceptively simple: when the elements are arranged in order of increasing atomic mass, their properties repeat at regular intervals. Lithium, sodium, and potassium behaved alike. Fluorine, chlorine, and bromine shared a family resemblance. A rhythm emerged from the noise. The true power, however, lay not just in the horizontal rows but in the vertical columns, which grouped elements with similar chemical personalities. His system was not merely a list, it was a map. The initial response was muted. A quiet curiosity, mixed with heavy skepticism. His colleagues saw an elegant pattern, a neat intellectual exercise, but many doubted its practical worth. The most audacious feature of his table drew the most scorn: the empty spaces. Mendeleev had deliberately left gaps in his grand design. These were not errors. They were placeholders. He claimed, with an unnerving certainty, that these gaps represented elements that humanity had not yet discovered. This was a leap from classification into prophecy. It was one thing to organize the known world, it was another entirely to predict the unknown. He gave these phantom elements provisional names, borrowing the Sanskrit prefix eka, meaning one. There was eka boron, eka aluminium, and eka silicon, each named for the known element sitting one position above it in the table. From the logic of his system alone, he began to describe them. He was a cartographer drawing coastlines of continents no one had ever seen. For eka aluminium, he laid out a startlingly specific profile. Its atomic mass would be approximately 68. Its density would be around 6 grams per cubic centimeter. It would be a metal with a high melting point, forming an amphoteric oxide. He even predicted how it would react, what its salts would look like, their crystalline structure mirroring those of aluminium. To a scientific community grounded in empirical data and experimental proof, this seemed like sheer fantasy. It was an assertion of faith in a pattern over hard-won laboratory fact. His confidence was almost arrogant. He even dared to correct the accepted atomic mass of tellurium. According to the best measurements available, it was heavier than iodine, yet Mendeleev's system demanded iodine come after it. He switched them, insisting his structure was right and the measurements were wrong. For years, the gaps remained just gaps. The table was a powerful teaching tool, printed on large wall charts for universities and schools, helping students see chemistry as a coherent system rather than a chaotic collection of facts. But to many researchers, its predictive power was an unproven and unlikely hypothesis. Then, 6 years later, the news arrived from Paris. A French chemist, Paul-Émile Lecaque de Boisbaudran, was analyzing zinc ore samples. Using a spectroscope, he detected spectral lines that belonged to no known element. He had found something new. Through painstaking work, he isolated the substance, a soft, silvery metal. He named it gallium, in honor of his homeland. As he documented its properties, a remarkable picture emerged. Gallium's atomic mass was 69.7. Its density was 5.9 g/cm superscript 3. Its oxide was amphoteric. The predictions Mendeleev had made from nothing but a belief in his pattern, a ghostly echo of his theoretical EKA aluminum. Mendeleev immediately penned a response, a clinical, point-by-point comparison of prediction versus reality. The atomic mass differed by less than 1%. The oxide properties were identical. The chemical behavior matched his description completely. He pointed out that this discovery wasn't just about a new element, it validated the entire system. The dam of skepticism had been breached. 4 years later, another crack appeared. In Sweden, chemist Lars Fredrik Nilsson was painstakingly working with minerals from Scandinavian deposits when he isolated another new element, scandium. Its atomic mass was found to be around 45. Its properties were typical of a light, rare earth metal. Once again, the scientific community turned to the chart. There, in another empty square, was Mendeleev's prediction for EKA boron. The properties were a perfect match. Then, in the mid-1880s, the final proof arrived from Germany. Chemist Clemens Winkler, while analyzing a rare mineral called argyrodite, found a third unknown substance. He named it germanium. It was a semi-metal with an atomic mass near 73 and a density of about 5.5 g/cm superscript 3. Its character was a strange hybrid, blending metallic and non-metallic traits. It was exactly as Mendeleev had described EKA silicon. By the dawn of the 1890s, the three most prominent voids in his map of matter had been filled. They were not filled by chance, but with elements whose existence and characteristics had been deduced from pure theory years earlier. Science hadn't just gained 3 new substances, it had gained proof that an objective, underlying order governed the chaos of the natural world. The reaction from the global scientific community was a seismic shift. The table, once dismissed by some as a convenient teaching aid, was now hailed as a powerful predictive model, a guide for future exploration. Invitations poured in for Mendeleev to speak at international congresses. His papers were translated into German, French, and English. Leading scientists across Europe and America wrote about his astonishing foresight. Where doubt had echoed just a decade before, there was now a chorus of admiration. Yet Mendeleev himself did not celebrate. He felt no sense of triumph, only vindication for the logic he had trusted. In his correspondence, he repeatedly emphasized that he was no prophet. "I did not discover the elements," he wrote. "I only indicated where they should be. And if they were found there, it means the table is correct." Personal glory was secondary, what mattered was the confirmation of a fundamental law of nature, a logic that grew from the substance of the world itself, not from fashion or assumption. Back in Russia, the periodic table began to be taught not just as a part of chemistry, but as a masterpiece of the scientific method. Young instructors told their students not only about the properties of copper or sulfur, but about how a single mind, through structured thought, could leap ahead of empirical evidence. The very idea of prediction, which would become commonplace in 20th century physics, was first realized in chemistry on that single sheet of paper. Awards and recognition inevitably followed. Mendeleev received the Demidov Prize, was inducted into various academies, and was honored with the gold medal of the Paris Academy of Sciences. But for him, these were merely side effects of his service to science. He continued to refine the table, tracking new discoveries, re-evaluating disputed atomic masses, and campaigning for reforms in scientific education. His table was a living organism, growing and expanding while retaining its elegant structure. With his system internationally recognized, Mendeleev's restless mind, accustomed to seeking patterns, began to look beyond the laboratory. He saw no division between theoretical knowledge and practical utility. To him, they were two sides of the same coin, service to progress. He turned his attention to Russia's burgeoning industries, seeing chaos and waste where others saw profit. One of his first targets was the oil industry. In the 1870s, a black gold rush had begun in Baku, on the shores of the Caspian Sea. But the methods were primitive. Crude oil was often simply burned in furnaces or dumped. Mendeleev traveled to the Caucasus on an expedition, personally inspecting the operations. He descended into shafts, spoke with workers, and analyzed samples. What he saw horrified him. Locomotives were being fueled with crude oil. To his mind, this was insanity. He famously declared, "Burning oil is the same as firing a stove with banknotes." He argued passionately that oil was not a fuel but a precious chemical feedstock, a source for dozens of valuable substances from kerosene and lubricants to dyes and explosives. In a series of articles, he called for the construction of sophisticated refineries, the training of chemical engineers, and the development of advanced distillation science. He urged Russia to stop exporting its raw crude and instead process it at home, creating value and jobs. His proposals were radical, but his logic was undeniable. The man who had organized the elements now sought to organize the very engine of a new industrial age. But that was only the beginning of his quest to apply the laws of nature to the fate of his nation. His quest to organize the world did not stop at the ground. Mendeleev next turned his gaze to the sky. He became obsessed with aeronautics, convinced that the future of navigation lay in the vast, open air. For an empire as immense and roadless as Russia, mastering the sky was not a novelty, it was a strategic necessity. He dove into the physics of flight, meticulously calculating the lift of a hot air balloon, factoring in atmospheric pressure and temperature changes across the sprawling imperial territories. He participated in discussions for military aerostat projects, drafting principles for their control and submitting detailed reports to engineering departments. While the age of the airplane had not yet dawned, his rigorous calculations and visionary arguments formed a crucial part of the intellectual foundation for Russia's future aerodynamicists. He saw a network of airships conquering the tyranny of distance that had always defined his homeland. From the boundless sky, he returned to the most fundamental of human constructs, measurement. Mendeleev was appointed head of the empire's main chamber of weights and measures, a seemingly mundane post he transformed into a crucible of national reform. He understood a truth others missed: a nation that could not agree on the length of an inch or the weight of a pound could never build a modern world. It was a recipe for fraud, inefficiency, and scientific stagnation. He launched a sweeping campaign to standardize every unit of measurement, championing the adoption of the metric system. He personally traveled to workshops, verifying the master standards for length, mass, and volume. He wrote instructions, delivered lectures to surveyors and merchants, and waged a quiet war against the chaos of localized, traditional measures. Without precise, universal units, he argued, fair trade was impossible, industrial production was unreliable, and science itself was crippled. His work was so thorough and transformative that it gained international recognition as a model for how to systematically order the commercial and scientific life of an entire country. This drive for order was a philosophical mission. He saw Russia as a grand project in desperate need of a scientific blueprint. He published relentless articles on economics, education, and statistics, proposing radical reforms. He called for the creation of technical colleges to bridge the gap between science and industry. In an era of rigid patriarchy, he demanded that women be given access to higher education. He fought to overhaul the gymnasium curriculum, arguing for fewer hours of Latin and more physics and mathematics. "Our people are clever, but they are not learned," he wrote with a sense of urgency, "and without learning, there is no true reason." Science, he repeated endlessly, was not a luxury but the prerequisite for Russia's survival as a great power. He believed scientific literacy had to begin in the youngest classes, supported by popular journals and translated texts, a project he personally championed by editing magazines and reviewing new books. His vision was not for a soulless, mechanized state. He insisted that technology must serve culture, that science must have a moral compass, and that industrial production must not be thoughtless. The foundation for any reform, he believed, was a respect for the individual, for truth, and for labor. But this very commitment to free and honest inquiry would soon put him on a collision course with the state he so desperately wanted to save. By the early 1890s, the political climate in Russia was chilling. The Ministry of Public Education began to assert suffocating control over the universities. Student gatherings were restricted. The content of lectures was scrutinized. Professors were instructed to follow approved programs without deviation. For Mendeleev, who had taught chemistry for decades as a method of thinking, not a collection of facts, this was an intolerable assault. He had always encouraged independent thought and experimentation. The university was a sanctuary for the search for truth, not an administrative department for dispensing state-approved dogma. The conflict reached its breaking point. A series of student protests erupted, challenging the police presence on campus. Mendeleev did not condone the unrest, but he refused to condemn his students. He openly declared that violent suppression would only deepen the wound. He stood with them, defending their right to be heard against the brute force of the administration. He sent a petition to the ministry, a plea for reason. His resignation was not a retreat, but a declaration. Mendeleev found himself unchained from the ideological battles of the university, free to pursue work that was concrete, its results measurable and independent of political dogma. He had never joined a party, published a pamphlet, or spoken at a rally, yet his insistence on intellectual freedom was a profoundly political act. He maintained that a scientist must be independent, that truth outranks position, and that conscience is more valuable than a career. In this spirit, his departure became a symbolic act of civic dignity. Offers of other professorships and administrative posts arrived, even a veiled suggestion of membership in the Academy of Sciences, but they all came with strings attached. He refused every single compromise. The most painful chapter in this new life was his relationship with that very academy. Despite his monumental achievements, recognized across the globe, he was never elected a full member of the Imperial Academy of Sciences. The official reason cited his lack of a formal classical education, a flimsy excuse that fooled no one. His contemporaries saw it for what it was, a toxic cocktail of professional jealousy and bureaucratic intrigue. He accepted the rejection with stoic dignity but did not hide his bitterness. Truth does not need seals and orders, he noted in a letter. It shines by itself, if a person is not afraid to hold it openly. This philosophy guided his every action. Though exiled from his university pulpit, he became a moral authority for a new generation. Young researchers sought his counsel. Engineering societies, educational congresses, and local councils invited him to speak. His lectures, now held outside university walls, were packed to capacity. He spoke not only of chemistry but of Russia's future, of the scientific community's responsibility, and of the transformative power of knowledge. Russia will be elevated not by its numbers, he often said, but by its knowledge. His fate was a testament to how high principles can lead not to rewards, but to isolation. Yet it is in such isolation that a person can become a symbol. He threw his relentless energy into the industrial and physical challenges of the age. He wrote about oil and coal, proposing plans for modernizing production and transport. A project that captured his imagination was the creation of an Arctic icebreaker. Convinced that Russia must conquer the northern sea route, Mendeleev participated actively in designing a new class of ship. His precise calculations on mass distribution, hull shape, and coal storage were instrumental in the construction of the Yermak, the first Russian Arctic icebreaker, launched in 1899. Even with government commissions, he remained a scholar at his core, thoughtful, focused, and demanding. His day began early with a walk, followed by hours at his writing desk, surrounded by books, instruments, and notebooks. Everything had its place. In his study, the walls were covered with maps, diagrams, and portraits of the giants on whose shoulders he stood, Lavoisier, Newton, Lomonosov. He wrote everything by hand, often rewriting a text several times, meticulously polishing his style, searching for the perfect word, rejecting any hint of vagueness. As the 20th century dawned, his health began to fail. Chronic lung disease plagued him, but he refused to slow his pace. In 1900, he directed the Russian pavilion at the Paris Exposition, a task for which he was awarded the French Legion of Honor. By now, the periodic table had proven its genius. Letters arrived from all over the world, some addressed simply to Saint Petersburg. To the scientist who predicted elements. He was racing against time. He felt chemistry standing on the precipice of a revolution and he wanted to be ready. In his final years, he obsessed over expanding his great map, trying to find a place for new elements like uranium and speculating about those yet to be discovered. He pondered the nature of the ether and the structure of the atom itself. He knew his work was not finished. The winter of 1906 was harsh. His illness progressed, but he continued to write. Until his last days, a draft of his table lay on his desk, its empty cells waiting promises of future discovery. On January 27, 1907, Dmitri Mendeleev died in his apartment. At his funeral, there were no icons, only his students carrying a massive banner bearing the image of the periodic table. One of them held a simple sign that read, "He organized chaos." His death marked the beginning of his work's second life. Soon, the table was expanded with the noble gases. By the mid-20th century, the actinides and lanthanides found their homes. Quantum physics arrived to explain its profound structure, the energy levels, orbitals, and electron shells that he had intuited but could not name. In 1955, American scientists named the newly discovered element 101 Mendeleevium. Today, the periodic table is more than a schoolhouse poster. It is the foundation of material science, a universal language used in biochemistry, astrophysics, and engineering. It hangs in the laboratories of NASA and on the walls of rural schools. It is a symbol of the hidden order governing our world, a ladder leading from hydrogen to the heaviest elements, from observation to prediction. Mendeleev left behind not just a chart, but the radical idea that the universe is fundamentally knowable. He proved that a single mind, committed to truth, could stare into the bewildering chaos of existence and draw a map. What hidden patterns are we still failing to see?